Thank you, Martin. Well, ever since the theoretical concept of neutron stars was formulated, as well as the experimental observation of neutron stars, their connection to supernova explosions and the remnants that are formed in those explosions has been made many times. And the connections touch on many of the things that we've already heard on in parts of this conference. And the connection between neutron stars and supernova remnants is both broad and very, very deep. So like the Grand Canyon, you're not going to get through it in a 30-minute walk here. I'm going to try to show you some nice overviews and great glimpses to tell you why you need to do the full excursion, or why we all need to do the full excursion. So it's already been mentioned. In fact, I first looked at this and thought that I had a copy of Christian's slide here. These are all the things that we have as connections between supernova remnants and neutron stars. And we've seen throughout parts of this, and we're going to hear more about the fact that by looking at supernova remnants, we've identified an entire zoo of neutron stars. Some of those haven't been identified in supernova remnants. Many of them have. Similarly, thank you. By looking at supernova remnants that have neutron stars associated with them, we've learned a lot about different types of supernova remnants as well. Those lead us in the direction of understanding the explosion mechanisms that we heard about in the last session. Those include things like asymmetries, nature of kick velocities, and the structure of the interior structure of the neutron stars themselves. And an example that I won't spend much time on, but an example is a plot here from a paper by Laura Lopez and collaborators, where they started to investigate supernova remnants and look at their morphologies, kind of attacking this question about asymmetries and explosions, and made a separation of those that are core collapse, and all the ones that I have circled there are ones with neutron stars. So that's how they identified them. They looked at supernova remnants. They said, these have neutron stars in them. They're clearly core collapse. There's a couple of other ones on there that were done by their compositions. And they made measurements of the, essentially the elongation and the mirror asymmetry of the brightness distribution of those supernova remnants. And these are all the type 1A supernova remnants. These are all the core collapse ones. And you can see that they bifurcate very naturally, indicating that the core collapse supernova remnants have more evidence for elongated elliptical sort of behavior, possibly associated with asymmetries in the explosion. Although, as I will point out, and I'm going to skip this plot, but it actually kind of does make this point, that interactions with the dense and complex surrounding interstellar medium plays a big role there as well. But that's the kind of type 1A remnant you get, and these, that's the extreme case of the geometry of the core collapse ones. So, whoops. We already heard about this a little bit, but we know from radio studies from over a long period of time that the neutron star population is a high velocity population. These things get large velocities when they're formed. We also know from radio studies that there is evidence that the alignment between the kick velocity and the spin axis is not completely random. It's not a highly significant correlation. It's sort of like 3 sigma that it is not random. Clearly not all aligned, but nonetheless that gets to the whole formation mechanism. And connecting the kick velocities to the origins in supernovae themselves leads us to some observational connections between neutron stars and supernova remnants. So, for example, in this in a paper that is representative of a number of papers that invoke asymmetric ejecta distributions in the explosion as a means of imparting momentum to the neutron star and giving it a large kick. This paper shows results of something referred to as a tugboat effect, whereby a large amount of the ejecta mass is kicked out with high velocity, high momentum. Some of the ejecta is slower moving in the opposite direction, obviously. And the neutron star the proto-neutron star at that stage is in the environment of this more slowly moving mass and is actually gravitationally tugged along and accelerated in that process. And the prediction of this picture would be then that the bulk of the ejecta, the bulk of the ejecta momentum, is anti-aligned with the direction of the kick of the neutron star. This is just a parameterization in a paper by Thomas Janka just recently showing roughly what kinds of kick velocities could be obtained in these asymmetric ejecta explosions, where the primary parameters of interest here are the asymmetry parameter and the explosion energy, both of which are things that one can potentially put constraints on from observations of supernova remnants. On the other hand, it's also been put forth that the kick to neutron stars could come from anisotropic neutrino emission. In that scenario, in this simulation by Fryer and Kosenko, the anisotropy kicks the neutron star to the right. That, in their simulations, enhances convection in this region and actually allows the explosion to be more efficient over here. And so the ejecta are more prominent in the direction of the travel of the neutron star. So completely opposite of what the other scenario had. In addition, in this picture, this neutrino emission is purported to occur along the magnetic axis, which, if we assume it's not co-aligned with the spin axis, tells us if that neutrino kick is slow relative to the rotation speed. So imagine this thing gets to rotate around many times while this is kicking out the back end. That would end up having the kick velocity along the spin axis. On the other hand, if the kick is very, very short, then it will be somewhat random depending upon how long it is. If it was instantaneous, then presumably actually along the magnetic field line. Those are the kinds of things that one can study neutron stars in supernova remnants to try to constrain. So I'm going to give you a couple of examples of and return to specific supernova remnants to demonstrate how those kinds of information can be probed by the observations of neutron stars and supernova remnants. This is a remnant called G292.0 plus 1.8. It has a pulsar. It's located right here. That pulsar has a period of 135 milliseconds. If you zoom in, this is a Chandra image. If you zoom in on it, you see that it has a jet torus type structure. So that lets us infer that this is the spin axis of the neutron star, okay? And measurements of the optical ejecta in this supernova remnant by Frank Winkler and his collaborators, where there are many, many different knots for which velocities have been measured, allowed them to identify what the kinematic center of the explosion was based on those knots, as well as the free expansion age of the supernova remnant based on those velocities and the location of that center, okay? And so what one finds from that is that there's that kinematic center, there's the neutron star, so that separation plus the kinematic age of 3,000 years allows one to determine that the velocity of that neutron star in the plane of the sky is 440 kilometers a second if at 6 kiloparsecs. In addition, you can see just from the diagram that I've drawn here that I hope I don't burn this laser pointer out while I'm doing all of this, but the spin axis is this way, the kick velocity is this way. They are most certainly not aligned. And of course, there have been particularly early on when there were observational constraints placed on spin kick alignments, examples that made it look like this was a prominent phenomena. The crab pulsar is moving close to the direction of its proper motion. The Vela pulsar is as well. There was some modeling done by Roger Ramani and Stephen Ng, or actually I think it was Stephen who did the modeling, showing a number of systems that seem to have such alignment. This is clearly one that does not, and it's not alone in its in that sense. This is an example of one that doesn't live in a supernova remnant, but it's too nice to not show. It's the Geminga pulsar and its pulsar wind nebula. This is from work by Bettina Passelt, who's right here. And all I will say about this is that our work on this, which I think Noel Klingler will say more about on Thursday, and Oleg may as well, indicates that these are actually jets, as in this illustration here, and we know that Geminga is measured, is moving in that direction. So this seems to be another clear case of the spin axis and the proper motion not being aligned, in fact, quite unaligned in that particular case. Going back to G292, its pulsar has spin down characteristics measured. The supernova remnant has a good age because of its expansion ejecta measurements. And we know that for a neutron star with a constant breaking index n, that its age is represented by this expression, where this is the initial spin period right here. Okay, so we can make plots of the initial spin period as a function of age of the system for different values of the breaking index to figure out what its initial spin would have been. And what this shows you is that for breaking indices less than 3, which we've heard earlier this week are measured in quite a number of young neutron stars, the initial spin period for this pulsar was relatively short, and it could have been quite short depending upon exactly what that breaking index is. Of course, it's crucial to note that that breaking index may not be constant. The magnetic field may evolve, as we heard earlier today. It may have multiple multipole moments that make that a complicated thing to consider. And Samara will talk, I think, cover some of that aspects in her talk on Thursday. Another important thing that one can infer from this is something that I mentioned early on. Most of this material, virtually all of this material that you're seeing here, with the exception of this bar across the center, is supernova ejecta that has been heated from the reverse shock of the supernova remnant. And so one can, by taking the expansion center that I mentioned to you before, one can actually just take the dipole moment of the emission to see which way it points. And so that's what, you can't read this very well, this is a paper by Holland and Ashford, and it really, although it says that it was in 2077, it was actually just this year. And what they find is that the emission dipole moment is in this direction, which is just saying that it's brighter on this side than this side, basically. But that's the direction of the pulsar that we already talked about. So in this particular case, mapping out the distribution of the ejecta, let's say inferring the momentum of the ejecta by virtue of its brightness, would indicate that the spin and the kick are not aligned. I would point out, and I will get to this again in other places, that the brightness of the ejecta does not necessarily tell you where all the ejecta is or how it's distributed. If the ambient medium outside the supernova remnant over here is higher than it is here, the reverse shock will come in faster and earlier and light up the ejecta, and it can make it look like that as well. So we have to be really careful about how we infer these results. These are other results from that same paper, still in 2077, amazingly enough. And this one, and that one for sure are asymmetric because of interstellar medium interactions. So take it with that knowledge when you walk away saying, geez, they're mostly anti-aligned with the direction of the ejecta. They are, but it's not completely clear that that's illustrative of the momentum distribution of the ejecta, or whether it's just how it's been heated by the reverse shock. Okay? Cassiopeia A is another supernova remnant, young supernova remnant, for which similar information has been gleaned. It has a young and oddball neutron star in the center of it, the first I believe, of the class that we refer to as central compact objects, because there's no better name than central compact objects for something you have no other idea about how it works. This one too has lots of information from the expanding ejecta in the optical and other wave bands. And so we know from mapping those ejecta where the expansion center is. And there's the neutron star. The expansion center is somewhere up here. The neutron star motion is in this direction, okay? We can, in the X-rays, this is another Chandra image, we can map out where different ejecta reside in the supernova remnant. Here's a big plume of iron. Here are some features of some sort of silicon-rich material, et cetera. And Huang and Lamming in 2012 from these data mapped out where the ejecta are and what they could infer for the total velocity of those ejecta. And the bulk of the iron is weighted down by this plume here, but for the total ejecta distribution, they found a net velocity in this direction, again, not well aligned with the kick velocity. So perhaps these are examples of ones that are not providing real strong evidence for the anisotropic neutrino kicks for those neutron stars. I would be remiss if I did not show that we know a lot about the ejecta distribution in Cassiopeia A. Tracy Delaney put together a data set consisting of X-ray ejecta measured from the infrared, outflowing optical knots, the position of the reverse shock by that sort of red ball there, and of course the white neutron star in the middle. And you can see that the ejecta are quite asymmetrically distributed. This is the sort of thing that provides very, very strong constraints on what the explosions that the people who are working on modeling the actual supernovae have to deal with and explain. And of course, all of that pertains to where that neutron star will end up as this evolves. Now, when we go to older systems, we can still find supernova remnants that have neutron stars in them and play the same sort of tricks that we're looking at here. We can look at where the center of the explosion is. We can look up what the neutron star is. We can attempt to estimate the age of the supernova remnant and then make estimates about which way it's going, how fast it's going, etc. This is a simulation that precedes the data that I'll show you next for a reason. This simulation is showing a supernova remnant that's evolving with a pulsar at the center that's moving upward, except that in the simulation, the pulsar sits in one place and the remnant moves down. Okay, but anyway, it's an upward moving pulsar, and it has a density gradient. The density is higher on this side than it is on that side. Okay, and so the way that this evolves is that the remnant expands this way. It's getting farther on that side than that side because this is higher density. This is the pulsar. This is its nebula around it. And this reverse shock here is coming back in through the ejecta. So, like I said before, if you look at this thing right now and pretend that it's a real supernova remnant, a bunch more of the ejecta have been shocked on the upper right here than on the lower left. And it has nothing to do with the fact that the ejecta were not originally spherically symmetric, because they were in this simulation. You also note that this reverse shock is about to introduce itself to the pulsar wind nebula, and it will continue to do so. And as this evolves, here at this stage, the entire pulsar wind nebula being driven by this young neutron star is being crushed. And the point is that when you look at this later on, and it's about to stop, this is what we're dealt with to try to piece together how this explosion unfolded. And it's not totally made up. That's the supernova remnant we were trying to model. There's its neutron star. There's its relic pulsar wind nebula that's been pushed off from the reverse shock going through. And the point is that this asymmetry in the interstellar medium, coupled with the actual motion of the neutron star, make it difficult to figure out what's going on. And this, of course, is not new news. It's not new news. A paper by, I will butcher this, I would say Natick or Natick, but I don't really know how to pronounce that person's name, and Petrick in 1999 showed simulations of the same thing, a supernova remnant expanding into a density gradient, and showing, as you would expect, as time goes on, the supernova remnant is sort of offset from that center. It's expanding more in this direction. But what they show here with this dotted curve is that if you plop down a circle on top of the thing, it looks pretty much circular. It's just got a circle with the center in the wrong place, and that makes it very difficult to figure out what's going on. So here's a simulation just like the one that I just showed you. The center of the explosion, this is where things blew up, okay? And if you turn this into a real observation and then you draw a circle around it and you say, where's the center of our supernova remnant? It's here-ish, okay? And, you know, yeah, it misses the edges a little bit, but they don't really look like perfect circles anyway, so this is, as observers, what we would have done. And we see the neutron star here, so we would say, okay, so that's how far it traveled, so I can get the velocity if I know the distance to this thing and if I know the age. And it's obviously going in this direction when, in fact, we know that it really went that way, okay? So it's a complicated process that we have to go through to infer the information that is so crucial to driving what we understand about supernova explosion models and how they couple to neutron stars. This is the last example of a recent measurement of one for which we actually waited long enough to not have to model it. We actually see in the X-rays that this asymmetrically disrupted pulsar wind nebula that we know has a star seen in X-rays right here is actually moving down in this direction. From what I've just described to you, you would infer that this is the estimated explosion center, but we have a lot of work left to do to actually figure out this whole system and whether that's the correct interpretation. I'd point out that there's another example of this in poster 54 by Sternen et al. On another supernova remnant that shows a neutron star with proper motion. So finishing up, there's another crucial element that I mentioned at the outset, which is that the young neutron stars in these supernova remnants are evolving as well. And the way that they evolve thermally tells us a lot about their interior. Sometimes it tells us too much about their interior, actually. So what I have here is a plot from a paper by Danny Page from 2014 that shows a list of young neutron stars and what their surface temperatures are as a function of their ages. These are the same data in these two plots, but this one is for heavy element atmosphere envelopes for the neutron stars, and this one is light atmospheres. all of the ones in circles are ones that live in supernova remnants, and so they get to this whole neutron star supernova remnant connection. The ages of these things come primarily from ages of the supernova remnants. And what you see is that there are some of these neutron stars that are far below what used to be referred to as a standard cooling curve. They're pushed down to cooler portions or cooler regions of this diagram that indicates that there was an onset of more rapid cooling in this particular scenario, potentially by virtue of a larger mass neutron star. It can be from the onset of any kind of rapid neutrino losses, from the onset of superfluidity of neutrons and such. The key that I want to make is the importance of the supernova remnant observations, and in particular, these ones in green here are all upper limits. These are supernova remnants that we just looked at saying, where's the neutron star? And we looked hard with Chandra with the highest X-ray spatial resolution that we can get, and we didn't find any of these supernova remnants. We didn't find any neutron stars in those supernova remnants, so all we could get is upper limits on their temperatures. And these are pushing the cooling models down quite a ways. Three things need to be said about that. One, maybe they're type 1A supernova remnants, because we don't know. But for all of them that we looked at to turn out that way seems unlikely. Maybe they all form black holes. Well, first of all, they're pretty perfectly normal looking supernova remnants, and as we heard this morning, the ones that form black holes, they either don't make remnants or they make kind of wimpy explosions, so that's not likely it either. The third point to make is that we had to push pretty hard to do this. You really need to have a higher sensitivity X-ray telescope to push hard to find out what's going on with supernova remnants for which we currently don't identify their neutron stars. I'll finish by mentioning Cassiopeia A. Again, this neutron star, it has a well-known age because we know the age of the remnant. And in 2010, Craig Heinke and Win Ho wrote a paper saying that they looked at the data from Cassiopeia A year after year and found that the temperature was declining. And not only was it declining, but which was kind of surprising, that it was measurable over only 10 years, but it was declining very rapidly. This led to more than one theoretical paper about how that might happen. This one by Page et al. Invokes neutrino emission from the onset of a superfluid neutron fluid in the very core. And for different values of the critical temperature, one can get these diversions from the standard cooling to hit a very rapid cooling track. And they found that they could explain the observed cooling fairly well with this particular value of the critical temperature. It won't surprise you that slightly different models for the equation of state and different models for how the onset of the superfluidity as well as superconductivity of the protons takes place, that one can fit the data with slightly different models as well. And so this is a paper by Ho et al. That does the same thing. This is really crucially important stuff because this is one of the youngest neutron stars that we know. And it's revealing to us something apparently incredibly important about the interior. Christian mentioned how it takes a year to run a simulation out to a second and how it's really hard work. And I don't know if I would characterize this kind of stuff as hard as much as I would consider it tricky. It's tricky. The cooling of the neutron star requires that you take each one of those observations and figure out what its temperature was. And that might sound easy, but the calibration of telescopes change with time. With the Chandra telescope, for example, there's a buildup of contamination on the window of the detector. The observations don't necessarily all have the neutron star in exactly the same place. Some of them are done, in fact, all of these up here are done with the telescope in or the detector in a mode that actually doesn't read out very fast, and so a bright source suffers pileup, meaning that sometimes it reads 2 photons of one energy and thinks it only got 1 of a higher energy, and that makes the analysis complicated, okay? So to look at that, and George Pavlov and Bettina Pasel have been doing this for a while, so to look at that in more detail, they took a look at only the data that was taken in what's called faint mode, which lets you do the best calibration, let's say, corrections, only in subarray mode, which means it used a little window that could be read out fast so that it didn't have significant pileup effects. And they only used, and the neutron star was in the same place on the detector in all of them. And so first of all, the fact that there's no, that pileup is mitigated changes the basic temperature they get, and that's not a big deal and it's not a big surprise. But what's important is that these 2 observations, and this is a third one that has not yet been published, but Bettina, I'm sure, is going to do that very quickly, seems to show that, yes, there may be some cooling going on, but it probably isn't as fast as what was considered. I think more work needs to be done on that. It's really important work because we can see what the stakes are in terms of understanding the structure of neutron stars. I'm going to close by just saying what I said before. These observations, particularly searching for neutron stars in faint neutron stars in supernova remnants, but also for measuring the details of their ejecta in X-rays, require highly sensitive telescopes with good angular resolution, and at present we're pushing up against the limit on this. We just, our groups here just found out that we just got awarded another Chandra observation of one of these nice pulsar wind nebula structures like Gaminga. The project that I summarized to you before, which I guess I don't have written down up here, took 15 days worth of data to study 3 pulsar wind nebulae. With the next generation high-resolution X-ray telescope that is being put forth as a U.S. mission, that would be able to be done in about 7 hours. That kind of thing is highly important for this sort of work. I'll leave with a summary. I don't think I need to say this all again, and I'll thank you and see if there's any questions.
Thank you very much for the talk. And any questions or comments?
About this wonderful G292 and velocity spin alignment. As mostly massive stars are born in binaries, then after the explosion, the orbital velocity can contribute. And in this particular case, is it possible to exclude the case that the progenitor was born in a very close binary, and so we are dealing with the intrinsic perpendicular case?
Not only is it not, yes, that's a very good point that I breezed right past, but certainly contributions from being in a binary are important in that respect. I will tell you that this right here, this bar across here, is circumstellar material that is clearly defining an equatorial region, and whether that's just from an equatorial wind in a single star or whether that's defining an orbit from a binary is not at all known, but that certainly could be the latter case, which would be important.
You mentioned correlation between kick velocities and spin axis, but this correlation could be affected by motion of progenitor stars. You know that some massive stars which are able to produce neutron stars has velocities up to 800 kilometers per second.
Yes, so if everyone didn't hear it, the point was that some massive stars have large proper motions themselves, and that needs to be taken into account when looking at the final velocity of the neutron star. And yes, you're right, for the low end of the pulsar velocity distribution, that would certainly be important. For 500-600 kilometer per second ones like the ones I shown, less so, but yeah, you're right. That certainly could play a role as well.
Okay, final question.
But you showed the figure with those upper limits, which suggest strongly that some neutron stars cooling possibly very fast.
Yep.
Yeah. So is that completely ruled out in those cases that maybe like at the age of 10 to the 4 years, the neutron star actually left the supernova remnant, and that's why you don't see it? It's just not within anymore. Or just the second possibility that came to my mind is that sometimes there are, there are some background or foreground X-ray sources. Could it be that, in some cases, it's not possible with certainty to rule out that one of those sources is a neutron star or not?
Yeah, so those are both excellent questions, Oleg. And so with regard to the first one, is it possible that it just escaped the supernova remnant? Our search radius for every one of those supernova remnants would have required the neutron star to have been traveling. This was a long time ago. This was part of David Kaplan's PhD thesis. 800, 900 kilometers a second, maybe 1,000. So it's not impossible, but I would say it's impossible for all of them to have been that, because they would have been all out on the high peak of the velocity distribution. So I think no, that's probably not the answer. As far as whether the point sources that are detected in the field, one of them could have been a neutron star and we just misidentified it, that is indeed possible, but that was what we did. We looked at all of the point sources that we could identify. We looked at optical counterparts. We looked at their properties and couldn't find any that we concluded were neutron stars.
Clarify, please, what can you say about observed pulsar velocities of order of 1,000 and even much more than 1,000 kilometers per second? Is it possible to provide them by ejecta asymmetries?
Say the last part again. Is it possible to?
Velocity more than 1,000 kilometers and even several thousand kilometers per second. Is it possible to provide them by ejecta asymmetry?
I think that you would have to ask somebody who does the modeling of the explosions themselves. There's nothing about the supernova remnant observations, I think, that could very well constrain that. If you looked at all of the ejecta in a supernova remnant and you believed that you could define what its momentum was, you could certainly sit down and ask the question whether by conservation of momentum you could get something as high as 1,000 or 2,000 kilometers a second. But that would be a very, very hard thing to get past me as a referee. Okay.
Very good. Then let's thank Patrick again and